I'm Daniel, and together with my colleagues Matt, Tyler, and Sean, we are the storage systems team at DigitalOcean. Our team maintains the persistence layer for our storage products, including managing dozens of Ceph clusters. And in this talk, we'll be looking at the tooling that we built to perform RBD migrations between our Ceph clusters. We'll go over 3 different tools, why we built them, and how they work. So, before we get to any of that, why do we have multiple Ceph clusters in the first place? Because if you have just one big Ceph cluster in every region, you don't need to worry about or solve the migration problem. But there's a few reasons that we opted to have more. So the first reason is that we want to control the failure domain in case something were to go wrong. Or if we have to do some maintenance on the cluster or an upgrade, we are able to do it at a smaller scale. Our operations won't affect every single customer that is on that cluster in a given region, just the ones that happen to be on that specific cluster that we're doing maintenance on. Of course, when we see that something goes wrong, we won't run the process elsewhere in the region until we're sure that we've fixed the problem. And when it comes to upgrades, a larger cluster with many nodes and OSDs is going to take much longer to upgrade than something smaller. So that's another reason that we try to keep our clusters small, especially for block. And aside from all of that, a single cluster is still a failure domain in that there are things that we can't control, like load spikes and networking issues, that can affect a given cluster, but not another one, even in the same region. Now, on that note, a second reason is that we deploy multiple clusters means that we can go with smaller clusters. That means it costs less to deploy a new block storage product in a new region, and once that fills up, it costs less to augment and deploy a new one. Just start a second one and move all creates over to that one. Now, adding hosts and racks to a cluster, doing that kind of an augment that we used to do in the past, causes a whole lot of spikes in latency, and block customers are really sensitive to that kind of problem. So we don't do that anymore, and instead just add new clusters to the region. Now, the third reason is related to the number of file descriptors that are at play on the hypervisor side, and reducing the number that we have. So a hypervisor can of course host many virtual machines, or droplets as we call them, and each of those droplets can have over a dozen volumes attached, and each volume needs to talk to a lot of OSDs in the cluster, so very quickly you end up with a whole bunch of file descriptors, and that can cause all sorts of problems. So we were asked by that team to reduce the number, to tone it down a notch, basically, and that's what we considered in our cluster design. Now, the fourth reason is that simply multiple clusters allow us to start from a clean slate every so often, which is a form of risk mitigation. With one big cluster in a region, you have to maintain that one Ceph cluster for what is very likely the region's entire existence, or even the company's entire existence. And so you're picking up that configuration and carrying it through many Ceph versions, many generations of hardware and configuration. But when you have multiple clusters, you have the opportunity to start new ones. Eventually, the old ones get decommissioned, and so you start fresh. So now you see that we really needed the ability to move between RBD images between our clusters in order to make this whole thing work. So we've come up with some tooling to help us with this. And it started with Gantry. Gantry uses the RBD mirror to do most of its work. It sets up 2 clusters in a region as replication peers, and then enables the per image mirroring option to get the image in the destination caught up. And once it's caught up, it does a demote, it promotes it on the destination, and then disables the mirroring, which clears up the image from the old cluster. And that's that process. In the vast majority of cases, this goes off without a hitch, and it's a really fast and even a really simple way to move images between 2 clusters. And with this, you can also get data out of an old cluster very quickly. And best of all, RBD Mirror even takes care of the snapshots for you. So this sounds great, but what's the catch? Oh, The catch is that with gantry, you couldn't move RBD images that are attached to droplets or VMs without first shutting down the VM. And gantry did at one point have the ability to do this. There were times that we did have to use it, but obviously it isn't ideal to be shutting down customers' droplets in order to move between our clusters. So that's when we decided that it was time to build a new tool. And that tool is called LVOS, Live Volume Migration Orchestration Service. I didn't name it, but that's what we call it. And what this does is it uses QEMU block jobs, which were something that we already had available to us. This allowed us to build a new live migration solution without having to reinvent the wheel. Essentially what it does is it creates an identical sized RBD image on the destination cluster and sends an API call to libvirt to launch a QEMU block job. So this block job then begins copying data over from the source volume to the destination while still allowing the virtual machine's writes to go through. And with a recent configuration change that we made, the virtual machine's writes get sent to both the source and destination at the same time while the data is flowing between the two. And that recent change allows us to guarantee convergence. Now, when this component detects that the migration has converged, it will send a command to libvirt, tell QEMU that the VM can now primarily read and write from the destination. We keep the old RBD image on the source, archived for a few hours, and then eventually gets cleaned up by our tooling. Now, all of this, as you may have noticed, is coordinated by the VM. It's coordinated by QEMU. It's not a perfect process by any means. Because of that, it adds latency that the customer might see. But it's obviously way better than having to shut down customer droplets in order to move images. So it has been a lifesaver and raised our ability to manage Ceph clusters to a whole new level. Now at this point, we still had to manually put in volume names that we wanted to move, right? It still was a manual process. And now we had two different tools that we could use, so it started to get a little complex with thousands of possible RBD images that we could move. We needed to simplify the process a little bit. And that's why we built a third tool called C-Level. And what C-Level does is it detects variances in cluster fill, specifically clusters that are getting a little bit too full. It can pick volumes to propose as part of a batched migration job. And then once approved, it will send those volumes off to either the LVOS or gantry tool, depending on whether they are attached or not. It's one click to begin a job and start moving data. We can tell it also to not just look at fill, but empty out an entire cluster at once. And so it will, over the course of hours and days, propose new and new migrations until that old cluster has been completely emptied and has no RBD images from customers. So obviously, like, this tool isn't nothing groundbreaking, but before that we were sending off manually TXT files filled with volume names. So compared to that, this has been making our lives a whole lot easier to automate that process. As you can see, the proposal messages end up in Slack, and it's one click to invoke an approval and get the process to start. So really quickly, as a review to which tools that we have LVOS, Live Volume Migration Orchestration Service, that helps us to move RBD images that are attached to a VM. The second tool, Gantry, which uses RBD Mirror to move the unattached images. And then the third tool, C-Level, that we just went over, quickly get the image names and send them off to either tool. So our migration capabilities have come a long way in just the past few years. What's next? Going forward, we want to look into ways to reduce the latency impact that running LVOS has on the customer. So that would be a good thing that we want to spend more time investigating. And then the other thing that we wanted to do is build out tooling that moves customers between different tiers of block storage, if that is the place that we want to move our product portfolio towards. So that about wraps it up. Here's a quick hiring plug with a link to our careers page, and that's my presentation. pass it off to the next presenter. Yep.
So is the LWAS quite similar to the QEMU live migration in the sense that it doesn't shut down the VM at all, right? It just introduces latency. So instead of the QEMU like having small down moment of milliseconds, this wouldn't have that.
Yes. My understanding is that QEMU's live migration of VMs and its live migrations of volumes or storage volumes is quite similar in the background, but that is way down at the QEMU level.
I see.
Yeah, and we're just orchestrating those jobs, sending them off to the hypervisor.
Yeah, so the LWAS is like, so it isn't built on the QMAU, right? This is another tool similar to that.
Yes, so it's our own tool that we built in Go.
Yep.
It doesn't actively like handle the bytes of data itself. Rather, it sends jobs to start to libvirt, which then ends up in QEMU.
Okay,
so there's like several layers below LWAS, actually, when it comes to doing migrations.
Yeah. Thank you.
Thanks for your question.
Do the QEMU block jobs have an effect on like CPU use on the hypervisor host? Like, do they have a noticeable effect on the performance of the hypervisor host?
It would have some effect. There are several options that we can tweak to potentially reduce that effect. One of the things that we've looked at is using I/O threads, where I/O ends up on a dedicated CPU thread so that the other cores of the CPU aren't busy with the block job.